Welcome back to Physics 142. So we've been talking about electric potential, and we just showed that the electric potential for a point charge is kq over r. And we also know that if we know potential energy, we can calculate potential by just dividing by the charge of whatever the object we're considering as potential energy. And we know that there's a connection between electric field and the path that you walk through an electric field and the change in potential. This is very similar to sort of work done, right? There we do force over some path changes your energy. Here, electric field over some path changes your potential. Now, before I get to generalizing this formula to many point charges in a continuous charge distribution, I want to step back and see if we can think a little bit more about if we can visualize this concept of electric potential a little bit. All right. And I do that because I tend to think about electric potential as in my head as sort of like hills and valleys. And let's see if I can explain that a little bit with maybe an example. So what I'd like to do is I'd like to first think about some sort of uniform electric field. Let's draw a uniform electric field here. All right. And so here's my uniform electric field. And I want to think about some different spots in this electric field. All right. So let's think about a spot here, maybe a spot here, spot here, and maybe a spot up here, and another spot maybe right down here. All right. And let's just go ahead and number these 1, 2, 3, 4, and 5. All right. And let's think about what is the amount of potential, the relative amount of potential of these sources. So the first question we might ask is which of these sources has the highest value of the potential? So, well, how do we think about that? We talked last time that if you walk in some path along an electric field, right? So if I walk and I take a bunch of steps along the electric field, or maybe, let's start here at 5 and I take a bunch of steps dl along this electric field, then EDL is going to be a positive dot product because I'm going in the direction of the electric field. And it's always the opposite of that. So what that would suggest is that I would lose potential as I go along the electric field, right? That's what we get with this formula. If EDL is positive, if they're going the same way, then I'm going to lose potential. So what that says is that 5 must be at the highest potential, right? Or thinking about it the other way, so you could sort of think about walking along this electric field line here. It's sort of like walking downhill, right? You're losing potential as you go downhill, just like you might lose gravitational potential energy going downhill. So if 5 is at the highest potential, another question we might ask is, are there any of these points that are at the same potential? All right. And well, yeah, if we think about it, if you walk sideways, perpendicular to those electric field lines, well, then when you take this dot product, you're going to get a cosine of 90, right? The dot product of things that are perpendicular is 0. And so 1 and 4 have the same amount of potential. And we could think of them as being sort of the same height on a hill here, right? And so we could write that 1 and 4, those have the same potential. So there's a concept that comes up sometimes is people will talk about equipotential surfaces. And an equipotential surface is just any sort of region where you have the same amount of potential. So anywhere along this line here would be an equipotential surface. And you could think of it sort of like a contour line on a map of height, right? Contour lines would show a bunch of spots on a hill that are all the same height, right? Maybe you've seen a map where, they say maybe this is 10 feet and this is 5 feet, and maybe here is 1 foot, right? And this would map sort of the height of the hill, right? Similarly, so all these contour lines, they're lines at the same height. Those would be equa height lines. So, because it's all the same height. And here we have, this would be a line of equipotential. So, let's think about maybe a positive point charge. A positive point charge, the electric field goes radially out from that positive point charge, right? You can draw some electric field lines going radially out. And so if we wanted to draw equipotential surfaces, what would they look like? Spots that all had the same potential. Well, that would be lines that are perpendicular to the electric field lines, and that would be circles around this, right? This would be everywhere along this circle would have the same value of potential. Everywhere in here would have a higher value of potential. Everywhere here would have a lower value of potential. But everywhere along that circle, that would be an equipotential surface. If instead we had a negative point charge minus Q, right? Your equipotential circles would still, or the regions of the same potential, it would still be a circle, right? The circle would still be perpendicular to the field everywhere. But notice that negative charges, those are like walking downhill, right? You'd be walking down into a valley. So negative charges give you negative potential. And that makes some sense with our formula that we have here, right? That if we put in a negative Q, we'll get out a negative V. If we put in a positive Q, we'll get out a positive V, right? So negative charges create sort of valleys, while positive charges create hills, is a sort of a way of visualizing potential, all right? Another way of thinking about this might be to say that as you walk along an equipotential surface, you do no work. Whereas if you walk closer to a point charge, then you're doing positive work, right? You're going up, then you're going uphill, right? And if you walk toward a negative charge, you go downhill, right? So, all right. That's just a little summary that maybe gives us a little bit better sense of how to think about potential. I like to think about it as hills and valleys, all right? And that you always are going from that positive charges, going up field lines, that's going to positive, down field lines, that's going to negative. The electric field lines sort of tell you the slope. Electric field lines are always going to point downhill.